Hello and welcome. Today we are doing a question from LeetCode called Sum of Left Leaves. It's easy. Let's get started. Given the root of a binary tree, return the sum of all left leaves. A leaf is a node with no children. A left leaf is a leaf that is the left child of another node. Example 1, we have the root node 3, then 9, 20, 15, and 7. So here our leaves are 9, 15, and 7 because they have no left or right children. But our left leaves are only 9 and 15 because they are the left child of another node. 9 is the left child of 3 and 15 is the left child of 20. So we sum up their values and output 24. Example 2, we have just the root node 1. So while this is a leaf node, it has no left or right children. It's not a left leaf because it's not the left child of another node. So there's nothing really to add up here and we output 0. So this is pretty straightforward. What we need to do is find all the leaves in our tree and also check to see if they are the left leaf. If so, then we just need to sum up all their values and finally output that. Now this is a tree problem, and I say this before every single tree problem, but it's really important that you know how to traverse a tree. I have my binary tree in order traversal linked down below. If you haven't already seen it, give it a watch. I cover both the recursive and iterative approaches on how to traverse a tree. So DFS and BFS. Watch that if you haven't already. It's just such an important concept to know because you're going to be using it for any tree problem that you come across. Go watch that. It's going to take 5 minutes, and if you're still watching this video, I'm going to move forward with the assumption that you already have that knowledge. Now for this question specifically, we want to sum up all the left leaves. So we want to go down the tree and find all the left leaves. For this, we want to go down, which means we are going to be using a depth first search. And to do that, we are going to approach this recursively. A quick recap on what a recursive approach is. It involves two parts. One is the base case. That means our endpoint, when do we stop, and what do we return there. And the second part is our recursive case. This is where we actually put the logic together. And before we get into all of that, let's just take a closer look into example 1. So I have example 1 right here. And for any tree, we are going to start at the top, the root node 3. At any node, I have 3 pieces of information. I know what my value is, and I know what my left and right children are, if any. So at this top node right here, I see that I have both a left child and a right child, which means I am not a left leaf, and there's really nothing for me to do at this point, and I can continue traversing through both my left and right subtrees. Say I go down my left first. I am at node 9, and I can make checks to see whether or not I am a leaf. So I have no left child, I have no right child, that means I'm a leaf. But how do I know that I am a left leaf? Because the only other information I have at this point is my own value. So something we can do is when making a call, so when 3 calls 9, for example, we can pass in a flag, a simple true or false boolean that is true if I am calling my left child. Otherwise, it would say false. And we can just keep calling this in our recursive call. And if that flag is true and I have no left or right children, that means I am a left leaf. But instead of doing all of that, there's actually something else we can do that's much simpler. We can move all our checks an entire level above. So at node 3, I'm going to see if I have a left child. If I do, I'm going to see if that left child does not have any left or right children, in which case that is a leaf, and I know it has to be a left leaf because I just checked on my left child. In that case, what I'm going to do is return the value of my left child and continue going through my right subtree. And if I don't hit that dead point in which I both have a left child in that left child's left and right children are none, then I'm just going to go through both my left and right subtrees as normal. So let's go ahead and code all of this up and then go through it line by line to really see how this recursive call stack is being built. So the first thing we want to see is our base case. What if my root is none? If there's nothing being passed in, what do I want to return then? So if root is none, I know I want to return the sum of all left leaves, and this is just my base case. The actual logic of the addition will be happening in my recursive case. So here I just need to return some number, and I'm going to be returning 0 because there's really no left leaf value that I need to return here. And when am I not going to be returning 0? Well, that's when I actually have my left leaf. So if root.left, so if I do have a left child, and root.left is none, and root.left right is none. So I do have a left child, and that left child does not have a left child, and that left child also does not have a right child. That means I have a left leaf, in which case I want to return its value. So return root.left.val. Now, I want to return the value of my left leaf, but there's still my entire right subtree that I haven't gone through. So yes, this is a stopping point for my left side, but I still need to continue going through my right. So I'm going to be returning the value at my left leaf and recursively call, so self.sum of left leaves on root.right. And if I don't really run into this left leaf, then what do I want to do? I want to return the self-sum of left leaves on both left and right children. So root.left plus self.sum of left leaves on root.right. And that is it. So let's go ahead and run this code. Accept it and submit it. And it is accepted as well. But before leaving, let's go through an example and see what our code is doing line by line. Okay, running through an example, we're going to be taking a look at example 1 again, and I'm going to change it up a little bit just so we can go into all the conditions. This is my input tree, and I start off with the root node 3. I'm calling this function sum of left leaves with 3. So calling it with this. What am I going to return here? Well, the first condition is to see if my root is none. It is not none, it is 3. I'm going into the second one. If root.left, do I have a left child? I do, it's 9. And root.left.left is none. 9 does not have a left. And root.left.right is none. 9 also does not have a right. So all of these hold true, which means I am in this return. I'm going to be returning the left.val, which is 9, plus recursively calling sum of left leaves on my right child. So sum of left leaves on 20. This means that now I have to recursively call on 20. I'm going to be going in this function again with root node 20. So what do I return here? With 20 being called in, I'm back into this function. My root is not none. And I go make these checks. If root.left, it does exist, and root.left.left is none, which is true. And root.left.right is none, that's not true because my left does have a right. So I'm not going into here, I am out of these two if blocks and going straight into this return, where I return the recursive call on both left and right children. So I'm calling sum of left leaves with 15 as well as 7. And we read and evaluate left to right, so I'm going to be calling 15 first. With 15, I'm back in here, my root is not none, and I'm making this check. I actually don't have a left child here, so I'm already out of this if condition, and I'm just calling this. So at 15, I am calling the sum of left leaves on my left child, but we know that's none, so it's actually going to be calling it on none, and my right, which is 4. So again, we have to evaluate left to right. We have to call the none before we can solve for 4 and continue back up. And if you see, this is how our recursive call stack is being built. So calling now with none, I go back into this function and I see that my root is none this time, so I'm going to be returning 0. So I can actually exit out of here and return 0 for this call. Now I can evaluate for sum of left leaves at 4, so calling this function again with the input 4. My root is not none, it is 4, and now I'm making a check if root.left, 4 does not have a left, and I am in this return right here. So here I am calling sum of left leaves on root.left, which is none, and root.right, which is also none. So here again we have to solve for the left one first. So I'm calling this again with none, but we know that none is going to be returning 0. So I can exit out of this call and return back to my caller with just 0. And again, we're going to be making this call for 4's right child, which we know is going to be 0. It's going to be another call with none, and we're going to get 0 for that. So at 4, I'm going to do 0 plus 0, which evaluates to 0. So at 4, I am completely done. There's nothing else to solve for, and I return to my caller with 0. So at 15, I have a total sum of 0. That means all the left leaves in this subtree is 0, which makes sense. There is no left leaf at 15 or 4. So I'm going to return back to the caller of 15, which was 20, with 0. And now we have to call again with 20's right, which is 7. So calling with 7, what am I going to return here? Root is not none. We're going to be making this check, and I know 7 does not actually have a left child, so I am in this return right here. I am going to be calling this with none. There is no left child of 7, and this with none again. There is no right child of 7. And when calling with none, again, this is just going to output 0, so I can pop this off. I am done solving for this. This is simply 0. And this is also 0 over here. At 7, we have 0, and we're going to return this back to our caller to just be 0. At 20, we have 0, and we can finally bubble back up to our original caller with 0. So 9 plus 0 is just 9, and all the left leaves in this tree sum up to 9, because we only have the leaves of 4, 7, and 9, and the only left leaf is 9. And this is how we solve sum of left leaves. Talking about space and time complexity. For time, because we're going through every single node in our tree, that would be O of n if there are n nodes. And same with space, right? If there are n nodes, potentially our recursive call stack could go n deep, so that space is also O of n. If you have any questions at all, let me know down below. Any comments, any questions. If not, I will see you next time. Bye!